Hello, welcome everyone. This session is composed of a lecture delivered by Professor Juliana Vizzotto, who works at the Department of Languages and Systems of Computation, as well as the Technology Center for the Federal University of Santa Maria in Brazil. Um, she holds a PhD in computer science that was awarded by the Federal University of Rio Grande do Sul, and in 2007, um, her doctoral thesis received the third place in the Brazilian Computing Thesis Contest provided by the Brazilian Computing Society. Her talk is entitled Symmetric Pattern Matching and Quantum Control. Thank you very much for accepting our invitation to talk here. Be welcome, and I pass it on you.
Okay. Hello. First of all, I would like to thank you, the Quantum-Latino organizer, for the invitation to talk about my work on quantum computing, more specifically about quantum programming languages. So I'm very happy to be here today. I'm present here. I joined work with Amr Sabry from Indiana University and Benoit Valiron from University Paris Sud. So our thesis is basically that we define a purely quantum programming language, including some notions of quantum control. The structure of control flow in classical programming languages is well understood. However, in quantum programming is still a new intricate subject. So our language is essentially motivated by the notion of symmetric pattern matching and reversible languages. Here I have the roadmap of the talk. So I'm going to start to talk about quantum control. For that, we are going to discuss the models of computation we can consider and the notion of control in quantum programming. Then I'm going to mention some previous approaches in the context of quantum control paradigm. And finally, I'll show our approach based on pattern matching isomorphism. So from one point of view, the quantum algorithms can be considered as classical algorithms having access to a quantum memory. Considering this perspective, the control flow notions of sequence conditionals in loops and recursion are classical. And the quantum program can be seen as the construction, manipulation, and evaluation of quantum circuits. So I'm starting with some preliminary concepts. So the quantum memory, in the example here, the quantum memory has 3 qubits. With a normal condition, and unlike probabilistic distributions, all are available at the same time. So the stream of instruction on the quantum circuit model is given by a series of elementary gates applied on the quantum memory. In this example, the wires indicate the quantum bits, the quantum memory, and the gates are unitary and reversible. There is no quantum loop, conditional escape, or branching point. We can have circuit combinators for repetition, inversion, and the controlled operation. Here I have an example of a controlled circuit with a conditional action. Like say the gate C is applied on the qubits 2 to 4 only when the qubit 1 is true. Then suppose that C flip its input bits, then the above circuit turns the qubit in superposition to this qubit. That is, the bits are flipped if the control is 1. So this acts as a quantum test that we will formalize. So the control flow of the program is on the classical computer. So it generates the quantum circuit that will be executed in the quantum memory. So the idea is to work the notion of control flow that itself quantum. So moving control inside the quantum memory. We have distinct behavior on each distinct state in superposition, and we have the notions of quantum tests and the notion of quantum loops or fixed points. And so quantum control is a long-term objective to work with quantum control, is to understand the structure of quantum operations and to have a syntax for building circuit combinators. And some challenges: the preservation of unitary, norm, and orthogonality of states. Here I have an example of a quantum if called if zero in the KML language style. So the idea is to allow superposition states in the guard and have the two branches executed in parallel. So here we have to pay attention to the coherence, is important here, and to norm and orthogonality of states. No quantum termination, that's unlike probabilistic behavior, all branches are available. So measure of success for capturing quantum control: compilation to circuits and model the operations as unitaries in some Hilbert space. So I'll talk about some previous approaches briefly. Oh, sorry. Here I have a table with some characteristics like concrete syntax, recursive types, higher order, orthogonality and norm, quantum tests, and quantum loops. Some characteristics we want to have in a quantum programming language with quantum control. So we bring here some previous approaches that inspired our work, like KML, quantum lambda calculus, linear algebraic lambda calculus, Ying's quantum loops, circuit description languages, and our approach. Then we compare. Like KML, we have a concrete syntax, orthogonality and norm, and quantum tests. In the quantum lambda calculus, concrete syntax, higher order, orthogonality and norm. So linear algebraic lambda calculus, no, just don't have orthogonality and norm. Ying's quantum loops, orthogonality and norm, quantum tests, and quantum loops, and circuit description language, just higher order. So inspired in these works, our approach tries to reconcile all these characteristics. So quantum control flow, quantum tests are fine, can be done with regular control, and quantum loops are the main roadblock. So as I told, our work is inspired in expressive languages like linear algebraic lambda calculus, in approaches to loops in quantum programming as the work of Ying's, and preservation of unitary, like EML. So our approach tries to reconcile these features. So I will start to talk about our language with pattern matching and quantum control. So the most elementary control structure in programming languages is the ability of conditionally execute one of several possible code fragments. However, expressing such abstractions using predicates and nested if expressions makes it difficult for both humans and compilers to reason about the control flow structure. Then, instead, in modern functional programming languages, the conditional control is elegantly expressed using pattern matching. This approach yields code that's not only more concise and readable, but also enables the compiler to easily verify the following two crucial properties: non-overlapping patterns, exhaustive coverage of the data type using collection of patterns. Indeed, most compilers for functional languages perform these checks, warning the user when they are violated. At more fundamental level, like in type theories and proof assistance, these properties are actually necessary for correct reasoning about programs. So our first insight in this work is that these properties are sufficient to produce a simple and intuitive first-order reversible language. So then here, there is an example written in Haskell-like syntax. Haskell is a classical functional programming language. So I have a skeleton of a function f that accepts a value of type nat plus nat, and the patterns on the left-hand side exhaustively cover every possible incoming value and are non-overlapping. The function g accepts values of type bool times nat, and again, the patterns are of left-hand side are exhaustively cover every possible incoming value and are non-overlapping. So we claim that since the types nat plus nat and bool times nat are isomorphic, we can combine the patterns of f and g into symmetric pattern matching clauses to produce a reversible function h. We use the double arrow to indicate that the function can be executed in either direction. This reversible function is obtained by simply combining the non-overlapping exhaustive patterns of the two sides of the clause. And in order to be well-formed, these clauses are subject to the constraint that each variable occurring on the side must occur exactly on the other side. So these are conditions for the reversible maps, exhaustivity and non-overlapping. So here I have, So here I have the formalization of the ideas present in the examples. The language is two-layered. The first layer contains values, which also play the role of patterns. These values are constructed from the variables ranged over X, and the introduction forms of finite types A, B, constructed from the unit type, sums, and products. The second layer contains collection of patterns matching clauses denoting isomorphism. the type of double arrow B. So computation are chained application of isomorphisms to values. The typing rules are defined using two judgments for typing values or patterns and terms, and with a judgment with the W for typing collection of patterns, matching clauses denoting isomorphisms. So the most interesting rule is this one for isomorphism. The rule relies on two auxiliary conditions as motivated before. These conditions are orthogonality judgment, the orthogonality judgment, and that formalize the patterns must be non-overlapping, and the condition which formalizes that the patterns are exhaustive. So the language explained so far embodies symmetric pattern matching clauses as its core notion of control. So its expressiveness is limited, however. It's possible to extend it to have more common with conventional functional programming languages. So we extend the language with the ability to parametrically manipulate isomorphisms, with a recursive type of lists and with recursion. So the variable f expands the set of iso variables, and variable x expands the set of term variables. So we extend the layer of isos so that it can be parameterized by a fixed number of other isos. And we now allow higher order manipulation of isos, iso variables, and applications. And isos can now be used inside another isos using the let. So here I have some examples. We encode booleans as the type B, 1 plus 1, and true as left, and false as right. So we can define the function not, which flips a boolean, and a controlled not gate, which flips the second bit when the first is true. So here I have an isomorphism representing the not and the controlled not as an iso as well. And so by using the abstraction facilities in the language, we can define higher order patterns that build complex reversible functions from simpler ones. For example, we can define a conditional expression parameterized by the function using the two branches, like this if. So using the if and the obvious definition of identity function ID, we can define the control as control f if fid, and recover an alternative definition of C not as control not. So using higher order here and isos. And we can even iterate this construction using fixed points to produce, for example, an controlled not function that takes a list of any control bits and a target bit and flips the target bit if all the control bits are true. Down here is using the So here. So here we have the any control not function using the fixed point operator. The language is also expressive enough to write conventional recursive and higher order programs. For example, the map construction that is very common in classical programming languages. So we illustrate this expressiveness using the map. So that receives a function and applies this function to a list of elements. So these examples use fixed points, which are terminating in any finite context. That is, the functions are structurally recursive. Here is just. So we have reversible pattern matching, recursive types, higher order on isos, requiring that fixed points are terminating. So the reversible pattern matching, we have a syntax for in this reversible pattern matching language, you have a syntax for circuits with a plus and with sum and products, and a generalized notion of control. And following circuit description languages like Quipper and Quillwire, we add recursive types, for example, the lists, and higher order on isos. And we have fixed points, lambda abstractions, box in circuits, and an iso describes a bijective map on the set of values. Summarizing, so far we have a high-level reversible language, expressive enough, and now we want to turn the isos into unitary maps. So in the language an iso W, A double arrow B describes a bijection between the set of closed values of type A and the set of closed values of type B. These sets can be regarded as the basis elements of some vector space, and the iso W becomes a 0-1 matrix. For example, consider an iso defined using three clauses of the form V1 double arrow V1 prime, V2 double arrow V2 prime, V3 double arrow V3 prime. We can see that we can denote this iso as this 0-1 matrix. So the definition of clauses is, so we extend the definition of clauses to see isos as unitaries and not only as bijections on basis elements of the input space. We generalize the clauses to complex linear combinations of values on the right-hand side, with the side condition that the following matrix then is unitary. So the coefficients of the linear combination of the values in the right-hand side must denote a unitary matrix. So we are going to from classical reversible to quantum. We have linear combination of data as a side effect. So now, as in the linear algebraic lambda calculus, we have superposition as A plus B, as we have the superposition alpha left to plus beta right V, such that U is type A and V is type B, and such that left U and right V are orthogonal subspace. So in the finite case, we have finite dimensional space, and iso U A double arrow B yields then a unitary map A to B. And we have now superposition of clauses and preservation of orthogonality and norm. So for example, this allows one to define an iso behaving as the Hadamard gate, or a slightly more complex iso conditionally applying another iso. So here is the definition of Hadamard. with the condition that the coefficients of the right-hand side denote a unitary matrix, and here a gate that conditionally apply a gate, a unitary. Oh, sorry. And for example, we have so to account the limit elements, so we have we propose to use the standard Hilbert space L2 of infinite sequence with the condition that the fixed points are terminating. So general isos produces unitaries in L2. And I think my time is almost finishing. And the last example, a map Hadamard of type list of bool to double arrow to list of bool defined using the fixed point operator, applying the Hadamard to a list of elements mapping. So we have a syntactic notion of quantum loop with quantum termination. And so we propose a reversible language amenable to quantum superposition of values and with quantum control. The novel aspect of quantum control that we are able to capture here is the notion of quantum loops in a simple way. And these loops were believed to be hard. What makes it work in our approach is the fact that we are firmly in a closed quantum system without measurement. And I think my time is finishing. So thank you very much, and hope you had enjoyed the talk.
It's been a great talk. Thank you very much.
Okay.
There's a question here I would like to share with you from Gustavo Alejandro Paredes. He's asking the following. Is there any fundamental difference between quantum compilers and classical compilers? So in your view, what would be the answer?
Between quantum compilers and classical
compilers, yeah.
I think the difference is the machine you need to compile to the code. I think this is the main difference. The operations in the machine. I think
yes, I agree. Thank you.
Yeah.
I have a question actually about the what you mentioned about quantum loops, because that's a very tricky part about quantum programming.
Yes.
So would you mind elaborating a bit on that as for how you're thinking of solving that problem? Please?
The quantum loops. Yes. Here, like our approach tries to start to think about how to solve and to work with a structural recursion and terminating fixed points. I think maybe it's the start point, like to work with some start to work with some restrictions, and then to open the work for more generalized version of recursion.
Okay,
I think.
Thank you.
I don't know if you can, if it would be possible, but it's like to work with measurement in this approach. Maybe it's the next step.
All right. Yeah, I think we will invite you to talk about quantum loops next year. So,
thank you.
All right. Well, it's time now to finish this lecture. So thank you very much again for accepting our invitation for this great talk. I hope that you have enjoyed it as much as we have listening to your ideas and developments. And so as for the audience, thank you very much. This talk ends the morning session today. We shall come back in 20 minutes' time to listen to Professor Alana Spuro-Guzik, who's the keynote speaker of this day. So see you in, just a few minutes before 1 o'clock, Mexico City time, Bogota time, which is exactly the same time now. All right? See you in a few minutes. Thank you very much.
Thank you.